All right, just waiting for the charts to come up. There we go. Okay, so as Bill said, I'm going to be telling you about a project that we're running at NASA called NHATS, the Near Earth Object Human Spaceflight Accessible Target Study. Presenting on behalf of myself and my colleagues, Paul Chodas and Alan Chamberlain at the Jet Propulsion Laboratory, and I myself am from NASA Goddard. Okay, so a quick overview of NHATS. This is an ongoing collaboration between Goddard and JPL, the purpose of which is to monitor the accessibility of the known near-Earth asteroid population. We began this project in September of 2010 and fully automated the system by March of 2012. The system runs daily, processing newly discovered asteroids and those with updated orbit solutions. And all of the information is published on our NHATS website, which is hosted on NASA's Near Earth Object Program website. There's a searchable database on that website, along with a mailing list that folks can subscribe to. The website provides comprehensive mission trajectory calculations, plus the next available optical and radar observing opportunities for all of the near-Earth asteroids that meet the NHATS criteria. Now, the purpose of automating the system and having it run at a daily cadence is to provide rapid notification for observers, both optical and radar, because oftentimes the couple days, maybe a week or two, right around when a near-Earth asteroid is first discovered is also the prime time to acquire follow-up observations that tell us about the object's size, that allow us to better know its orbit, understand its spin state, and other things that are relevant for mission planning. This diagram here just provides us with a quick orientation for the types of missions that we're considering. Essentially, we start off at Earth. We assume that we're in some kind of a low Earth orbit. We depart from there. We arrive at the asteroid, so maneuvers are required at both of those points. We then stay on the asteroid's heliocentric orbit for some period of time. We depart the asteroid sometime later, and then we fly back to Earth. Once we arrive at Earth, if our reentry speed is too high, we'll have to perform an additional maneuver at that point to manage the reentry speed. So these are the constraints that are applied in the NHATS trajectory processing. I'm going to go over these numbers just to provide us with a background, but we won't really have context for what these numbers mean until a few charts from now. So we consider Earth departure dates between the years 2015 and 2040. We restrict the Earth departure energy, which is denoted commonly as C3, to be less than or equal to 60 kilometers squared per second squared. We restrict the total mission delta V to be 12 kilometers per second or less. As I mentioned on the previous chart, this includes a maneuver to depart a circular low Earth orbit at a 400 kilometer altitude, match the asteroid's velocity upon arrival at the asteroid's location, a delta V to depart the asteroid and initiate the trip home, and when necessary, a final maneuver to control the speed of entry into the Earth's atmosphere. We have a restriction on atmospheric entry speed of about 12 kilometers per second, measured at an altitude of 125 kilometers. That's the atmospheric entry interface altitude. For reference, the Apollo missions, the fastest Earth entry they recorded was just a little bit above 11 kilometers per second. So 12 kilometers per second is not something we can do now, but ideally will be something we might be able to do in the future. We also enforce a constraint that means that the spacecraft must stay at the asteroid for at least 8 days. The diagram, or plot rather, that's shown here on the right-hand side is referred to as a pork chop contour, or PCC plot. Sometimes the contours resemble cross-sections of pork chops, and so it's an old name with a lot of history behind it. But really what it shows us here is on the horizontal axis, Earth departure date, and on the vertical axis, round-trip flight time. And then the colors represent delta V, ranging from 3 to 12 kilometers per second, required to fly a round-trip mission to the asteroid with this particular departure date and some particular round-trip flight time. This particular graph here is for the asteroid designated 2000 SG344, which is currently the most accessible object under NHATS criteria. On this chart here, I'm just showing a screen capture of the NHATS website. It's It's a little bit hard to see at this resolution, but this is the data that's made available to you. If you visit the NHATS website, I'll provide the URLs a couple of charts from now. And what the table provides is a listing of all the objects that are compliant with the trajectory requirements that I just outlined. And then for each object, the database shows two optimal solutions, the minimum delta V solution and the minimum mission duration solution. The estimated diameter of the object is shown along with the next optical and radar observing opportunities for the object. And for radar, we show both Arecibo and Goldstone opportunities. The calculation of the next observing opportunities provided by my colleague Paul Chodas, and Alan Chamberlain wrote and implemented the website and the database. I maintain the computer system at Goddard that does the automated trajectory calculations and transmits the data to the server that maintains this database. So that's how we close the loop. I also maintain the mailing list that provides the rapid notification to near-Earth asteroid observers. This database is sortable and filterable, meaning that you can change the thresholds for total delta V, total mission duration, minimum stay time at the asteroid, the range of Earth departure dates you want to look at, the absolute magnitude of the asteroid, which is a proxy for size, and also the orbit condition code of the asteroid, which represents how well we know its orbit based on observational data collected thus far. And we can also sort the table according to any of the quantities that are shown here. So it's a very flexible interface, and based on mission requirements, you can quickly zero in on what group of objects may be available for a given combination of requirements. So this is the chart that I'll probably spend the most time on, and again, it's a very busy chart, and it's difficult to show at this resolution. However, it is available online at the SBAG website. The URL is shown here. So if you visit the SBAG website and you look at this so-called Science Nuggets section, which is a collection of basically one chart representations of interesting information about small bodies, you'll find this chart here. I update it every few months. The last time I updated it was June 7th of this year, so about 5 or 6 weeks ago. At that time, there were 1,211 near-Earth asteroids that meet the trajectory criteria that I listed previously. As of today's date, there are 1,221 such objects. So since June 7th, we've found 10 more. Every year, we discover about 1,000 new near-Earth asteroids. And so as we discover more near-Earth asteroids, we also find that some of those newly discovered ones meet NHATS criteria. And so the subpopulation of NHATS-compliant near-Earth asteroids continually grows. This chart here is meant to place the notion of accessible near-Earth asteroids into context. If I tell you that a near-Earth asteroid is accessible, you might ask me, well, what do you mean? Accessible compared to what? So what this chart shows is on the horizontal axis, round-trip flight time in days from 0 to 950, and on the vertical axis, total mission delta V from 0 up to 18 kilometers per second. There's a line drawn at 12 kilometers per second, and also a vertical line drawn at 450 days round-trip flight time. So this is kind of the NHATS box right here. These are just the constraints we enforce. There are plenty of asteroids offering opportunities outside this box. We're just not calculating their mission opportunities. So all of the NHATS near-Earth asteroids are these blue and green dots right here. And this green reference line shows the minimum delta V to just barely break out of low Earth orbit. So your delta V to go visit an asteroid in its native heliocentric orbit will never be any lower than this green line. And so the other points of reference on this chart have to do with the Moon and Mars. Down here, this little dot right here is the asteroid redirect mission's human portion that goes out and visits a captured asteroid in a distant retrograde orbit around the Moon. So that's about 4.5 kilometers per second, about 25 to 28 days round trip. Just above that, we have low lunar orbit, going to a low circular orbit around the Moon, which is about 5 kilometers per second, and depending on how long you want to stay there, could be a week or two. To go to do a round trip to the lunar surface is about 9 kilometers per second. That's right here. Similar time frame. And then all these points out here are various types of missions to Mars. Over here is what it takes to go to Mars if you want to spend 500 days on a highly elliptical orbit around Mars, but not touch the surface, and then come home. If you want to go down to the surface for those 500 days, your delta V is now up here. If you want to go into orbit around Mars for some other period of time, say 45 days, these points right here show what that costs. So higher delta V, but you're able to complete the round-trip mission in less time. And then these points up here are for staying in a highly elliptical orbit around Mars for a week and then coming home. And then these points down here are for just doing a flyby of Mars on a free return trajectory and coming back to Earth. So the point of the NHATS criteria that I listed before is that all NHATS-compliant near-Earth asteroids are more dynamically accessible than Mars. There are no Mars mission opportunities that fall within this box. But there are 1,221 near-Earth asteroids that do fall into that box. So the purpose of the NHATS, as I said before, is to keep an eye on this subpopulation of the overall near-Earth asteroids so that we can be cognizant of which ones they are and prioritize them just like we prioritize potentially hazardous objects in terms of collecting additional observations so that we can better understand their physical characteristics. And that'll help us select mission destinations in the future for any missions that may go to visit a near-Earth asteroid. So with that, I'll be happy to take any questions.
David Gump with Deep Space Industries. Since getting to Mars takes so much more time, have you thought about extending your criteria from 450 days to some larger number, because eventually a longer voyage will be necessary to get to Mars?
Yes, so we have a list of things that we would like to add to the system. It's just a matter of getting around to doing it. The other motivation for looking at longer duration round-trip near-Earth asteroid missions is, of course, for pure science missions, like the OSIRIS-REx mission, which is going out to the asteroid Bennu. It's launching in 2016, coming back 7 years later in 2023. So that's a 7-year round-trip mission, 2,500 days, something like that. So that would be, way off to the right-hand side on the plot there. So monitoring those types of mission opportunities would be valuable as well. Yes.
Good. Any other questions? All right, good. Thanks, Brent.
Sure.